A equals QR. This is one of the most important factorizations in numerical linear algebra. So what's it all about? Well, by definition, a QR factorization is an equation that looks like this. A, which is a matrix, equals Q times R. Here, A can be any m by n matrix, and let's say that the rank of that matrix is equal to the number R, the little r. So what are Q and R here? Q is an m by r matrix, so m here is the number of rows of A, and little r is the rank of A. And our stipulation, which is new for us, is that Q must have orthonormal columns. So orthonormal is a new adjective to us, and we'll need to say more about it in a moment. And the other ingredient in this factorization is the matrix R, which is an R by N upper triangular matrix. So when someone says this is a QR factorization, what they mean is that the matrix A that they are studying is equal to Q, which is a matrix with orthonormal columns, times R, which is any upper triangular matrix. So what does orthonormal mean? We say that a list of vectors, maybe Q1 up to Qm, is orthonormal if two axioms are met. The first axiom requires that the list of vectors is mutually orthogonal. What that means is that if you choose any two distinct vectors from the list and take the inner product of those two vectors, you're guaranteed to get 0. The second axiom that must be met is that the list of vectors must all be unit vectors. So what this means is that if you take the inner product of any of the vectors on the list with itself, you must be guaranteed to get the number 1. So I made a little typo here. This angle sign should be enclosing the two vectors together. So we say that a list is orthonormal if any two of the vectors are orthogonal to each other and each of the vectors is a unit vector. Of course, orthonormal lists of vectors are actually quite common. They're, as I'll try to argue to you, they're desirable to work with. For example, let's say we're studying R3. We can look at what's called the standard basis. This consists of the columns of the 3 by 3 identity matrix. So that's the vector 1, 0, 0, 0, 1, 0, and 0, 0, 1. Well, with this list of vectors, we can see that if we were to take the inner product of any two of them, we're guaranteed to get 0. And also, each of these vectors is a unit vector because each one has length 1. So this is maybe our first example of an orthonormal list of vectors. So whenever I think of an orthonormal list of vectors, I have this picture in my head, even though the coordinates of a general orthonormal list might be much more complicated than the standard basis. So why are orthonormal lists of vectors so desirable to work with? And why would I want to put them in the columns of a matrix? Well, it's because of this theorem. Let's say that a matrix Q is m by r, and let's say that its columns are orthonormal. It turns out that is the exact same thing as requiring that Q transpose times Q equals the identity matrix. So having orthonormal columns is equivalent to the equation Q transpose times Q is the identity, and of course Q transpose times Q is the Gramian. So in my head, matrices with orthonormal columns are the matrices whose Gramian is the identity. And the proof of this theorem is actually kind of fun, and I think this is useful because it helps us think about what the entries of the Gramian of any matrix look like. So to prove this theorem, what I want to do is I want to take a closer inspection at what each of the entries in the Gramian of Q would look like. So keep in mind, when we take Q transpose and multiply by Q, we end up constructing a symmetric matrix where each one of the entries is an inner product of one of the columns of Q with itself. So what is the 1, 1 entry of such a matrix? Well, if we're working with a matrix that has orthonormal columns, the 1, 1 entry is the inner product of the first column with itself, which has to equal 1 by the unit vector axiom. So that entry has to be 1. What if we go to the 1, 2 entry of the Gramian? Well, if our matrix Q has orthonormal columns, that entry has to be 0 because the inner product of the first column with the second column must be 0. And if we keep going down the first row, when we get to the last entry, we'll be looking at the inner product of the first column with the last column. And again, that inner product has to be 0 by the mutually orthogonal axiom. Then if we jump to the second row, the first entry will be the second column inner product with the first column. That has to be 0 by the mutually orthogonal axiom. Then when we move to the 2, 2 position, this is the inner product of the second column with itself, which has to equal 1 by the unit vector axiom. And if we keep going down the second row, we'll get to the last entry, and this entry is the inner product of the second column with the last column. Of course, that has to equal 0 by the mutually orthogonal axiom. And then we keep going down with this pattern. Whenever we see an inner product of 2 distinct columns of Q, we know that inner product must equal 0. So we keep filling those entries in. And then the very last entry we fill in here is the last column of Q inner product with itself, which has to equal 1 here, and that's the unit vector axiom. So we go through entry by entry looking at the Gramian of Q here, and what we're finding is that Q having orthonormal columns is the same thing as requiring that this matrix equals the identity. And so this is the proof of our theorem. So whenever you think of a matrix having orthonormal columns, I want you to think of that matrix having a Gramian that's as simple as possible. And what I mean by that is the Gramian equals the identity matrix. So let's look at an example here. So here we're looking at a 4x3 matrix. And so this is my Q here. And it's important to not forget about this scalar that's out front here, 1 over root 7. So the first column of this matrix is not -2, -1, 1, 1. The first column here is -2 over root 7, -1 over root 7, 1 over root 7, and 1 over root 7. And same goes for the other 2 columns. So that's my Q here. And if I wanted to check whether or not this matrix had orthonormal columns, the thing I would do to make that calculation efficient is I would look at the Gramian. So I would transpose my matrix and then multiply by the matrix. And I did the calculation here, and when I multiplied Q transpose by Q in this order, I got the 3x3 identity matrix. So and we can sort of see this calculation here. Like this 1, 1 entry is the inner product of -2, -1, 1, 1 with itself, and then we divide by root 7 twice. Well, -2, -1, 1, 1, inner product with itself is 4 plus 1 plus 1 plus 1, which is 7. And then if I divide by root 7 twice, I get 1. And so the idea is that we can keep, we can apply that calculation to each entry of the product here. And we get the identity matrix in this example. So the conclusion here is that the columns of Q are orthonormal because Q transpose times Q is the identity matrix. And here I've listed those columns individually. Now, it's also important to remember that just because we take a matrix and multiply by another matrix and get the identity matrix doesn't mean that the matrix is invertible. Here, we've taken Q and multiplied on the left by Q transpose to obtain the identity, but this is not saying that Q transpose equals Q inverse, because in this example, Q is not even a square matrix. So we have to be careful when we say that something is an inverse, because having an inverse means first and foremost that the matrix is square. So in this case, we can multiply Q on the left by Q transpose to get the identity, but because Q is not square, we can't say that Q transpose is the inverse.